We are into the third lecture, and today's topic is ensemble and phase space. In lecture 1, we have covered the basic concept of the difference between the three statistics MB, B and FT. In lecture 2, I have explained you macrostate and microstate and solved two types of numericals from macrostate and microstate. Now, ensemble, that is a building block of statistical mechanics. Ensemble basically means assembly. Like you had it in your school days that right from class 5 to class 12, all in the morning before prayer, all used to assemble. So basically ensemble means some collection. So so it's called the collection of large number of identical interacting macroscopic system. Suppose you imagine that on a football field, players are playing with referee and all. So if you take the video of that game or match and you take, say for example, you take a video of 6 seconds and then you have several softwares to cut down that video into snapshots, still pictures. So you will find that for that 6 seconds video, you will have the 6 seconds video will be converted. So every second you will have a still pictures. So when these still pictures are put it on the table together, so I can say this 6 pictures for 6 seconds for every second gives you information about the position or some other parameters, the state of motion of the players. But for every picture, for every second, the picture will have the same information about the number of players, their field, the referees, all this. So here if you consider that there are particles, many particles enclosed in a container of volume V, and say there are n number of particles and they are in motion. So when you consider this motion and if you record this motion in a video and then transform this video into still pictures, so say for example you have a video of 6 seconds and then when you transform them into, for every second you transform them into snapshots, it look like this. So every snapshots of the system gives you information about the state or position of the particle, but the macroscopic systems remains unchanged. So what I'm trying to say is, say for example in this case, so every second you have the picture, the position or the momentum or other quantum variables or other variables, mechanical variables, they might change, but say for example the volume enclosed, the number of particles or the energy, so these parameters will not change in each picture for each second. So this collection of pictures is basically called ensemble. Now there are basically 3 types of ensemble. One is called the microcanonical ensemble, canonical ensemble and grand canonical ensemble. So when you say this assembly, that means the collection of snapshots for a motion of particles, and then you transform them into pictures and then collecting those pictures, and for each picture if the number, volume and the energy, here n stands for the number of particles, v stands for the volume of the container, e is the energy, if for every picture the assembly of pictures So each picture will give information about something of the particles, where for each picture, if the number, volume and energy remain same, but some other parameters are changing, then that collection of information is called microcanonical ensemble. So I repeat, suppose if you have a large number of particles, they are in motion, but when you transform them into snapshots and then collection of those snapshots for every second, these information or these pictures will give informations, but each picture will have the same number of particles, volume and energy. Then this system or collection of this picture is called microcanonical ensemble. Why it is called microcanonical? Because every picture will have the same number of particles, information about the, suppose if you have 10 number of particles, for every picture you will have information about 10 particles. And the volume of the container, if it is say this many V, so each picture will have the same information about that volume, and the energy is fixed, or the energy, whatever the energy value, here also every picture will give the same information about the energy. So every picture will have the same NVE, but some other parameter might change. So this is microcanonical ensemble. We move to the next type of ensemble, which is called canonical ensemble. Canonical ensemble is like microcanonical, but it is where the assemblies will have the same number of temperature, I mean information of every snapshots will have same temperature, volume and number of particles. So like this, if you have particles in motion in a container, and when you transform them into snapshots, when the motion of video is transformed into snapshots, then this every snapshot will have information which is fixed, that is temperature, volume and number of particles. Maybe in this case, that if you transform them into pictures, every snapshots, every picture of gives information about the same temperature of the container, the volume is also constant, the number of particle is constant. It might happen that every picture will have different energies. So when you have the constant or the same value of T, V and N, we say it's canonical ensemble. We move to the third type, that is grand canonical ensemble, where it says that when you have the information or collection where each collect snapshots or each system or each picture will have same number of temperature, volume or same information about temperature, volume and chemical potential. Here mu stands for chemical potential. It says about chemical energy, or you can say chemical potential is gives free energy per unit mole. So I take you to the same motion of the particles. So if this motion of the particle is transformed into snapshots, then the transformation of each snapshot will have same information about T, V, mu same. But some other thing maybe here, it may be the number of the energy might change or number of particles might change. It might happen. So when you have the same number of temperature, same information about temperature, volume and chemical potential for every picture, we say it's a grand canonical ensemble. We move to the next concept, which is called phase space. This is a very important concept of in statistical mechanics. Phase space basically gives you a graph or a plot between momentum and position. So basically it describes the position and state of the motion of the particle. Suppose if a particle moves, suppose if you consider many particles moving in a box or in a container of volume V, and when the particle moves, so for each particle there will be a change in the position of, if you consider 3 dimension, there will be change in the position of X, Y and Z. For every X with time, if you change if there is a change in x with every time, then I can say that dx by dt will give me velocity in x direction. Similarly, dy and dt, dy by dt will give me velocity in y direction. Similarly, dz by dt will give velocity in the z direction. So I will have, for every change of the motion or position of the particle, there will be velocity in the x direction, y direction and z direction. So if you multiply by mass of velocity in x direction, you will get momentum in x direction. Mass multiplied by velocity in y direction, you will get momentum in y direction. And mass multiplied by velocity in z direction will give me momentum in z direction. So if I have a plot between momentum, that means the state of the motion, and the position, if you just consider a one-dimension motion, that means you have x and you have px. So you have x, and because of there is change in position, you will have velocity in x direction, multiplied by mass, you will get momentum in x direction. If you just consider that x is the position and px is the momentum, and if you plot position versus momentum, this is basically called the phase space. So for every position you will have a momentum, and the graph looks like this for the motion on the left hand side. Similarly, I can also plot energy and the position also. And but when you talk about three dimension, so for three dimension there will be x, y, z, which hints to the position, and for every x, y, z you will have momentum in px in three direction, px, py, pz. So basically for a three-dimension motion you will have six-dimension space, which is called the phase space. So you will have six coordinates. So for every particle, for a six-dimensional space, for every point on the graph, you will have six coordinates. Every coordinate you will have x, y, z, px, py, pz. So that's phase space. Now phase space we can classify into mm, uh, into two types that I will discuss later. Let me give you an example. For a one-dimension harmonic oscillator, simple harmonic oscillator means a spring attached with a mass, and this will oscillate, okay, to and fro motion, and because of this you will have the total energy. Potential energy is given by half kx square, where k is called the spring constant, x is the position. So this is a one-dimension example, and you will have kinetic energy where p is the momentum. So when you consider this case, and when you plot the phase space, you have the momentum in the y direction and x direction is the position, and the plot for this example looks like this. So this is the example phase space plot for one-dimension harmonic oscillator. So coming back to the type of phase space, so there are basically two types of phase space. One is called the mu phase space, another is called the gamma phase space. Now what is phase space? Phase space is basically a graph or a plot between position and momentum. So when a particle is in motion, for every motion, just for your understanding, you just consider one dimension. So if the particle is in motion, there will be change in x, and because there is change in x, there will be velocity in x direction. That velocity multiplied by mass will give you momentum in x direction. So if there are many particles in a system, so every particle will have x and px. If you plot x and px for every particle, the particles present in a container, then, and if you plot for all the particles, then what is mu phase space? In a system of many particles, a phase space is plotted, and then if a point represents for a single molecule, that means if you have set let us say if you have six particles in a container, so for every particle there will be a value of x and value of px, and when you plot that, so each particle, each point in this graph or phase space will give information about that particle. So if you have six particles, you will have six points on the phase space. So if this is the case, we say mu phase space. But when you have a system of say many particles, let us say for example 6 particles are there, and then if you plot, so every particle will have a value of x and px, and if you plot, and then each point on the plot will give information about all the particles, all the molecules in a system. So if you ask me then why are these, what are these points, why 4 points? If you say that 1 point means for all the molecules, then why there are 3 points? 3 points because for all the particles, if time passes, there will be, for every time there will be some change in x and px. So for all the molecules, if you consider the mean or the average value, you will have for all the molecules for a given time, you have a value of x and px. So this point basically means for a given time, the average or mean value of all the particles present in the system. Second point, this is for another time, but this point gives you information about position and momentum for all the molecules present in the container. So that is called the gamma phase space. Now again, coming back to this example of phase space, if you just consider this, so here if you consider the area of it, suppose, because in the next problem I'm going to tell you about the density of states, I'm going to discuss about density of states. So before I discuss the density of state, let me tell you that if you are asked to calculate the volume or area, so you consider this part where this is the area called, I mean to say that dx is the thickness and p is the length, so you can calculate the area. Why you need to calculate the area for a one dimension, but for a three-dimensional one, we say the density of states is calculated based on this formula. Density of states or number of quantum states, G. I will explain number of quantum states now, but density of states or number of quantum state is defined as volume in phase space within P and P plus dP divided by h cube. Now that is the definition. From there we have this formula. What does this formula say? Now the derivation from the phase space till here, the derivation is not included in your syllabus. You have only the theory of the density of states, and you have to understand what does this formula signify. Here G means number of quantum states. So what is this bracket P? P stands for momentum, and we don't say that G is multiplied with P, it is G as a function of P. What does it mean? It means that on the right hand side, the momentum value changes, the number of quantum state changes. Okay, and 8 pi V is the volume, they are constant, and H is Planck's constant, that is also constant. So let me explain you this formula. What does this mean? What does this formula means? But before that, I want to tell you that what is quantum state. Suppose you have in a container, say let us say 3 particles. Say 2 particles will have a momentum P. Let us say momentum of 1 unit. And then one particle have a momentum of say 2 unit. So I can say the first 1 unit, the lower momentum value as 1 unit, I can say P, and the next higher momentum I can say P plus dP, which is just as an example, you can say the next higher momentum is 2. So in a box, if you have 3 particles, 2 particles will have momentum P and 1 particle will have a greater momentum, which is P plus dP. Okay. Now if I say that how many particles are there in the first momentum, I will say 2, so I can say N is 2. If I say how many particles are there in the next momentum, you can say 1. Now what is quantum state? Now this particle, as you read it in class 12 chemistry, that what are the examples of quantum states? You read about principal quantum number, which means the shell K shell, L shell, M shell. So n is equal to 1, 2, 3 like that. You also had azimuthal quantum number, you also have spin. So these are the examples of quantum states. Now G is number of quantum states. What does it mean? It means, suppose you have, say, let us say that this particle is spinning clockwise and this particle is spinning anti-clockwise, and I said because of it is spinning clockwise, let us say it is +1, and it is spinning anti-clockwise, let us say -1. So you can say how many quantum states are here in this first momentum level. I can say there are 2 quantum states. So basically this is quantum states. Now what does this formula signifies? Suppose if you have a momentum p and you have a momentum p plus dp, next higher momentum. Now if anyone asks you that within this momentum, what is the within this momentum? It is obviously dp, the interval. So if this is say if this is p and this is p plus dp, the interval is dp. So within this interval of dp, change in momentum, what is the number of quantum states, or how can you calculate the number of quantum states? That can be calculated from this formula. So if you have a momentum interval and you want to calculate the number of quantum states, you use G as a function of P, means within that momentum your formula is 8 pi V P squared dP by H cube. So dP basically means that within that momentum interval. So now if I ask you that, suppose if you have energy levels E and energy E plus D. So you have 2 levels of energy. One is lower energy, which is called E. The other is higher energy, which is E plus DE. And you have, in the first energy level you have 2 particles, and in the second higher energy level you have 1 particle. And the energy gap, that means the energy interval, I can say as DE. So if I ask you that how will you, for this example, how will you calculate the number of quantum states? Will you use this formula to calculate it? I would say no. Why? Because this formula or this theory is for the momentum interval. If you look into this formula, it gives you information about momentum. So when you have a problem of one momentum to another momentum, within that momentum how many quantum states are there, use this formula. But when the problem changes from, if it changes to energy, so you have an energy level, you have another energy level, and within that energy level what should be the number of quantum state, you cannot use this formula. You have to reframe this formula. How to reframe this formula? Obviously you have to find out, or you have to transform this momentum information into energy, or you have to change the function momentum to energy. How to do it? So you have to think about some theory that connects between momentum, or have a relation between momentum and energy. So we already know that kinetic energy and momentum have this relation. This is from class 9. So if you want to recheck what you have done it in class 9, if you just substitute the value of momentum as mass into velocity in the left hand side here, you get m square v square. And if you bring this 2m to the denominator on the left hand side, obviously you will get half mv square, which is E, the kinetic energy. So you have this formula in class 11 as well as 9, a relation between momentum and energy. So why I'm thinking in this way? I'm thinking because I want to transform this function to energy. So I need a relation between momentum and energy. So I have p square is equal to 2me. What I will do, I will do the derivation on both sides. Will do derivative. So I will write 2p dp is equal to 2md, 2 and a mass of the particle will, because constant, so they are not derivable. Then what I have done, I cancel 2 and I get p dp is equal to md. Right? Now what I will do, just take on to the right hand side. 8 pi v, they are constant, they will remain like that. This p square dp I will write down as p into p dp. I repeat, p square dp, this entire thing I will write down as p into p dp. So when I write p, I can write root over 2me. How you are getting root over 2me? Because from this. So for p I write this, and for p dp, because I'm writing p squared dp, so 1p, for 1p I'm writing this, and for the next part p dp I write md. So when you substitute this value and this value on the right hand side, obviously you will find that except energy all are constant. And then obviously the number of quantum state now is a function of energy, because your momentum will get changed to energy, and then you will write g as a function of energy. That means the formula will look like this. So if you substitute the value of p and p plus dp here, you will get 8 root 2 pi v by h cube m to the power of 3 by 2 e to the power of half dE. So because now there's no, all the momentum has transformed into energy, and you can write the number of quantum state as a function of energy. So this, if you have this kind of problem where you are asked to calculate the number of quantum state as a function of energy, then you have to use this formula. So if you understood correctly, then I give you another question, that if you have, now we have discussed about momentum, we have discussed about energy. Now if you have in a container you have 3 particles, let us say 2 particles will have frequency nu means frequency, okay, and 1 particle will have a higher frequency than the 2 particles, other 2 particles. So let us say that frequency of the third particle is nu plus d nu, a higher frequency. Now if I ask you, within this interval of frequency d nu, what is the number of quantum state? Can you use this formula? No, because this formula means to calculate the number of quantum state as a function of momentum. But in this problem, you are asked to calculate the number of quantum state as a function of frequency. So what I have to do? I have to, like the energy in the previous slide, I have to transform the momentum information to energy, to frequency. So how to do that? I know that E is equal to mc square because I'm dealing with light frequency, okay, so I'm dealing with quantum particles, so I can write down E is equal to mc square as well as E is equal to h nu. This is Einstein's equation. Now so I can write, please observe this very carefully, I have mc square, c is called the velocity of light. So if you multiply 1c with mass, so m into c, so mass into velocity of light will give you momentum. So what you can write here, mass into 1c will give you p, and another c you bring it down. So I repeat once again, this mc square, you take m into c, that will give you momentum, I write down here, and the second c square you have, the second c you bring it down on the right hand side. So what you have a relation between momentum and frequency. Understood? Now so why I have done this? Because I want to change the information of momentum to frequency, because my problem asked me to do that. Okay, now because I have a dp term here, I have to change this dp to d nu, so I do the derivative. So what I'd have, dp is equal to h by c d nu. Why h and c? Because they are constant. H is Planck's constant and c is velocity of light. So what I will do now, I have the value of p, I have the value of dp, I will substitute here. So in place of p square, I will write h square nu square by c square, and in place of dp, I will write h by c d nu. After substituting these two values here on the right hand side, all the momentum will change to frequency. And obviously, you will have this on the right hand side as 8 pi v nu square by c cube d nu. So your momentum got transformed to frequency, and you use this formula for this problem when you are asked to calculate the number of quantum state as a function of frequency. Similarly, like energy, your number of quantum state no longer remains as a function of p or function of e, because on the right hand side all are constant except frequency, so you write number of quantum state as a function of frequency. So whatever we have done in lecture 3, so what what type of questions you can expect from this lecture 3 ensemble and phase space? So we have defined phase space, we have defined ensemble, we have defined types of ensemble as mu space, gamma space, types of ensemble as microcanonical, canonical, grand canonical. We have even derived the phase space expression or the number of quantum state expression in terms of momentum, energy, and frequency. Hope you understood. And then I end up lecture 3